All right, these are our notes on exponential functions, and today what we're going to do is we're going to focus on graphing exponential functions. So it starts with the warm-up of properties of exponents. So go ahead and do those problems, and then unpause the video and see how you did. All right, here are the answers, excuse me, to those problems. If you got any of them wrong or like all of them wrong, which would be not that great, I would highly suggest, looking into our last video or, Googling some problems or videos that you can look at on Algebra 1's exponent properties. Okay? All right, so what is an exponential function? Exponential functions are in the form f of x equals a times b to the x. So this is not anything new to us. Like, we know that geometric functions are exponential functions. So we've seen this before, right? And it says where b is greater than 0 and x is any real number. So in other words, b is not going to be negative and x is not going to be imaginary. Okay, so there's two basic types of exponential functions. We have exponential growth. So here is what exponential growth looks like. If you look from the left to the right, it is increasing, right? So as your x values increase, looking left to right, your y values increase. What the equation is going to look like is our y equals a times b to the x, and that b value is going to be greater than 1. So this value right here is going to be greater than 1. Okay? And that's what exponential growth is. For exponential decay, as we look left to right, our y values are decreasing, right? So if you look, as your x values get greater, your y values are getting smaller. How does the equation look on this? For your b value, remember, b is always positive. Your b value is going to be in between 0 and 1. A lot of times people refer to that as a fraction, but I don't like that because 3/2 is a fraction and it wouldn't work for this. So it's any number in between 0 and 1. Or that's what we're just gonna say. Okay, so let's go ahead and do 2 word problems, and then from there we're just going to graph. Okay, so this is what we can see what it looks like. And these, if you're in chemistry, this should seem very familiar. Or if you haven't done it yet in chemistry, it will seem familiar once you get to it. A certain cancerous tumor doubles in size every 6 months. If the initial size of the tumor is 28 cells and it goes untreated, how many cancer cells will there be in 4 years? Okay, so you can use a calculator to help you get these numbers. The first few you won't need it, but then like when it gets bigger and bigger and bigger, you might need it. But you of course can use a calculator to get these numbers for the fact that they're huge. All right, so after 0 years, 28. So when it first started, it was 28 cells, right? And then after 6 months, a half a year, it doubled. So that's 56. And then 6 months after that, it doubled again. So that's 112. 6 more months have passed, and it's doubled again, 224. Double that, 448. Another 6 months, 896. Another 6 months, 1792. Another 6 months, 3584. And then another 6 months after the 4 years, we're at 7,168 cells. This is called exponential growth. As your x values increase, your y values increase. Okay, there's also a common multiplier. The explicit formula for this example is, we've written an explicit formula for exponential growth before. We're going to use y equals. We're not going to do a sub n equals. We're going to do y equals. Or you could do something that represents cancer cells. You can do c equals if you want. Your initial amount, which was 28 cells. And then your constant multiplier, your r value, your ratio, which is 2 to the x power. Okay, so this is not x minus 1. We are, we start at year 0, right? So when you plug in 0, you get the 28. Your domain, so let's graph this actually before we state the domain just so that it makes sense to us. We have 0, 28, so these go by quarters here, so just like right there, let's say, oh, those do not go by quarters. That's like 250. So we'll do 0, 28 is very, very, very close to the x-axis. Then we have after 6 months, it is at 56. So that's hardly anything right there on that scale. And then 112, which is still not that much, because those are 250. So we're like here still. We're not growing much there, right? And then, is that 6 months? Yeah, okay. And then 6 months after that, we're at 224. So we're getting closer to there. Looks like a line so far, right? And then 6 months after that, right? These are going by 6 months? Yeah, okay. So that's at 2, we're at 448. So we're like here. And then at 2.5, we're at 896. 2.5, 896. So like here. And then at 3, we're at 1792. So we're like here. And then at 3.5, 3584. So here's this big jump. And then at 4, 7,168. So right there. Okay. I know that took me a long, not a long time, but a while to graph. But it was for the graph paper purposes. Okay. So usually that we could say we can continue to go forever in this direction, but this is a word problem and there is no time before that. It's starting at year 0. So it's starting here and then we're going to connect these and keep going. You don't stop there, but you keep going and then it goes on forever and ever. There we go. Smooth right there. Okay, so there's what your exponential function looks like. So since this is, and if you look, this is an example of exponential growth, but we were multiplying by 2 every single time, but the curve looks like this, right? Your y values are increasing. Okay, so we also want to do the domain. If this went forever to the left also, like if it didn't have any context to the problem, it would be negative infinity to positive infinity, but this starts off at 0, 0 is a value, an x value, and then it goes forever. And then your range, the lowest it goes, it's also, or sorry, the lowest your y values go. If you look at the graph, you're like, I can't tell what that is. But if you look at this, you can see the lowest your y values go, excuse me, are 28. And then it goes forever. Okay? All right. Next one, we have the half-life of caffeine in your body is about 6 hours. If you drink a cup of coffee with 140 milligrams of caffeine at 6 a.m., how much will you have remaining at 6 a.m. the next day? So 24 hours later. So half-life means that is the time that passes where only half is left. So it's saying the half-life is 6 hours. So if after 6 hours, half of this is left. Half of 140 is 70. Continue that. 6 hours later, half of that's 35. 6 hours later, half of that is 17.5 milligrams, and then half of that is 8.75. This is called exponential decay, because we're multiplying by half. Explicit formula, y equals our initial amount, 140, times 1/2 to the x power. All right, let's go ahead and graph it. So we have 0, 140, right there. And then 670. So we're right there. 1235, 12, 20, 30, 35. No, that's 30, that's 35. Let me erase this little dot here that happened too. Okay. 18 comma 17.5, so 18, and that's 10, 15, 17.5, and then after 24 hours, we are at 8.75, so like there-ish. Okay, I'm gonna start here, and then this is going to continue on, go forever. Okay, all right, so our domain here, looking left to right or looking at your x values, this is 0 to infinity because the time can go forever and ever and ever. At some point, this has an ending point to it, because at some point there'll be zero caffeine left in your body, or some people would argue that there's always a little bit left. And then your range, the lowest it goes is hopefully zero, right? We would argue that it goes to zero. Or we could say it doesn't include zero, because there'll always be a little bit left in your body. We can argue either one, but the highest amount is that 140. Okay, this is happening because of the word problem. If we took the word problem aspect away from it and just said just graph these equations, they would have a different domain and range. Okay, so next we're going to move on to graphing, and in order to do that, we have to remember what happens to a graph for each transformation. Okay, so we have to know what this means. If I had the function and I had a +1 on the end of it, what it means. So what I want you to do is I'll do A with you just to make sure we remember. And then I want you to pause the video and try the rest on your own, and we'll see how you did. Okay, so this right here, I have +1 on the outside of the function. So what this means to do is that I should do a vertical translation. Forgot to spell vertical for a second. Up 1. Or vertical shift up 1 is fine also. Vertical translation, vertical shift up 1. Okay? I'm going to change it to shift because pre-calc we use translation. I think we use shift in here last semester. So vertical shift up 1. Okay. So also while we're here, let's write a rule of what that looked like. It's a good idea to practice the rule. So nothing changes on x, but on our y value we would add 1. All right, go ahead and pause the video and try the rest on your own. And then you can fast forward through me explaining each one and see how you did. Or if you got anyone wrong, you can rewind and see, so on and so forth. Okay. So this is a vertical shift down 2. And the rule for that would be keep your x the same and then subtract 2 from your y's. This is a horizontal shift left 3. So we are going to subtract 3 from our x values, leave your y values alone. This is a horizontal shift right 4. So we would add 4 to our x values and leave your y values alone. Oops. I just realized that did I copy and paste something? Oh no. I didn't. Okay, good. Don't let me copy and paste anything, memory. Okay, because I have the last 2 for you to try on your own on there. Okay, sidetrack. All right, so next we have a multiplier in front of our function. So it's vertical since it's in front of your function. And then remember, this is either a stretch or a compression by 5. So that number is greater than 1, so it is a stretch by 5. S-T-R-E-T-C-H by 5. Okay, and what we would do there is we would multiply, oops, that's our x values. We'd multiply our y values by 5. Keep your x values the same. Here we have a vertical compression of 1/6. And we would multiply the y values by 1/6. So 1/6 y, or y divided by 6. It's however you want to write it. Oops, don't forget my little grouping symbol. All right, now we have a multiplier inside the function in front of x. So this is going to be horizontal, and it's the opposite of the last 2. So this is a horizontal compression, and it is the opposite of what you would think to do. You don't multiply the x values by 7, you divide them by 7. So x divided by 7, comma y. And then this is a horizontal stretch. Your x values, you're not going to divide them, you're not going to multiply them by an 8, you're going to divide them by 8, which is the same thing as multiply by 8x. Multiply the x by 8, and then leave your y alone. All right, here we have a negative affecting our function, so this is in front of the function, so this is a vertical reflection. So keep your x's the same, take the opposite of your y values, and then lastly, we have a reflection on the inside, so this is a horizontal reflection. So this is to remind us what to do when we're about to graph. So we are going to use transformations to graph. So that does mean that we're going to have to know what the parent looks like. So we're going to use points to get what the parent looks like. And then we will use those 3 points, because we're always going to have at least 3 points, to use our transformations to see what it looks like. Okay. All right, so here is an example of a parent function, a parent exponential function. F of x equals 2 to the x. It could be any number to the x. It could be a half to the x, 5 to the x. It could be 3 times 6 to the x, right? Whatever your base is on your exponential function, that's the parent, okay? So I need to know what this looks like, all right? So I need at least 3 points to graph this, okay? So I could plug in 300 points if I wanted to, but the points that I like to plug in, I'll make a table of values here. So actually, no, I'm just gonna write ordered pairs. The points that I like to plug in are the x values of -1, 0, and 1, okay? So when you plug in -1, 2 to the negative first is a half, 2 to the 0 is 1, 2 to the first is 2, and then I'm gonna graph those 3 points. So I have -1 a half, -1 a half, 0, 1, and 1, 2. So this is my exponential growth picture right here. And if you could keep going. If you plug in 2, you get 4, right? If you plug in 3, you get 8, right? And if I plug in -2, I get a 4th. And if I plug in -3, I get an 8th. You're never gonna get 0, and you're never gonna get a negative number. You're just gonna get closer and closer and closer to 0. So what that means is that there is a vertical asymptote at y equals 0. So we're going to draw that in, and then we can graph this graph. But now you know at least what we already know what it looks like. Ooh. We knew what it looked like, that we had that asymptote there, but now we can actually see where it is, okay? And it's one piece. I just can't continue and make points, apparently. All right, your y-intercept for this one is 0, 1. Domain, arrow to an arrow, all real numbers. Your range, the lowest it goes is that asymptote of 0, but it doesn't touch it, so parentheses, and then it goes up forever. The asymptote, once again, was y equals 0. So these next two, if you look at them, they also have a base of 2, and then it's to the x power, but then there's transformations done. So what we're going to do is we're going to write a rule. We're just going to transform them and then graph it using that. Okay, so our rule for this one, I'm going to write rule here, rule, so I know what it is. Okay, so if you look what's happening to your x values here, you have x minus 3, so that means that you're moving 3 to the right. So we're going to add 3 to our x values. Then we have this plus 2 on the end. That is, we're going to add 2 to our y values. Okay, so if you come back here, if you fast forward through this here is your parent function, a b to the x. You can have this plus h right here, and plus k, so that's your plus h plus k, just like we're used to using, right? So this is this right here. You're moving it right or left, but opposite of what you think, up or down, exactly what you think. Okay, so I kind of just stopped in the middle of that. So this one, we're going to add 3 to our x values, add 2 to our y values. What x and y values? These ones, because it was the base of 2, okay? So I don't like that okay, there we go. All right, so we're going to add 3 to the x value, all right? So that becomes negative, I don't want it in red, I want it in blue. -1 plus 3 is 2, and then add 2 to the y value, so that's 2.5, or 5/2. Add 3 to the x value, 0 plus 3 is 3, and I'm talking about this right here. Add 2 to the y value, 1 plus 2 is 3. I don't know why I'm putting these things on them. They're just ordered pairs, right? All right, there we go. Add 3 to the x value, that's 4. Add 2 to the y value, that's 4. All right, so I'm going to graph this new function. Now, my asymptote was at y equals 0, now it's at y equals 2. It's moved up 2. Right? And then I can graph these points. So 3, 3, actually 2, 2.5, over 2, 1, 2, up 2.5, right there. 3, 3, over 3, up 3, right there, and 4, 4. Ooh, look at that line disappeared, but I know it's supposed to be there, so 4, 4. How come that looks so strange? Add 3, add 2. I must have done something wrong. I have to fix it. Oh, that's really wrong, because I was looking at the x, I was looking at the asymptote as the y equals 0. Okay, so let's fix that. 3, 3 is over 3 up 3 right here, and 4, 4 is right here. Much better. Okay. There she is. She's gorgeous. Okay. All right, I still need my y-intercept. I didn't find it yet, so I got to plug in 0 and see what I get. So plugging in 0 here, I get 2 to the negative third, which is an eighth, and then 2 plus an eighth, which is 2 1/8. Or you can write it as 17/8. Domain, all real numbers. All exponential functions, as long as it's not a word problem, is going to have a domain of all real numbers. And then your range here is your asymptote up, and your asymptote was y equals 2. All right. Next one right here, still taking that y equals 2, the x and performing transformation. So I'm going to write my rule. All right, so this tells me to take the opposite of the x values, negative x, to reflect them. And then this tells me to move my y values down 4, so y minus 4. All right, looking back at these points again, the x value I'm going to take the opposite of. So the opposite of negative 1 is positive 1. And then I'm going to subtract 4 from the y value. So subtract 4 from that, you get 3 1/2. Negative 3 1/2, sorry. Take the opposite of 0, which is 0. Subtract 4 from 1, negative 3. Take the opposite of 1, which is negative 1. And then subtract 4 from 2, which is negative 2. Okay. My my horizontal asymptote was at 0. Now it's down 4, so I'm going to move it down 4. Okay, and then graph these points. 1 over 1, down 3 1/2, or right there. 0, negative 3, right there. Negative 1, negative 2, right there. So we have this. Now, you might be looking at this being like, oh, that's exponential decay. I'm doing something wrong. That negative exponent gave it a horizontal reflection, so it looks like exponential. So it does become exponential decay because that's 1 over, so that's 1 over negative. You can turn it into 1 over 2 to the x, and that's where you get that 1 over 2 from. Okay. Domain, or sorry, x-intercept, we already found it at 0, negative 3, so I'm not going to do it again. Domain, all real numbers. Your range is negative 4 to infinity. And then your asymptote was y equals negative 4. Voila. So if you haven't noticed, this plus k value right here, that's where your horizontal asymptote is, y equals k. Okay? All right, I'm going to do 2 more with you just because I've only done a base of 2 with you, and I wanted to show you that if it's a base of something else, you have to find the new parent, right? It looks similar. Exponential growth looks like exponential growth. Exponential decay looks like exponential decay, but it's not when you plug in 1, you get 2. It's when you plug for 3. It's when you plug in 1, you get 3, right? Okay, so my parent function is the asymptote's at y equals 0, and then the parent function for this is y equals 3 to the x. So my 3 points for this are plugging in negative 1, you get a third. Plugging in 0, you get 1. Plugging in 1, you get 3. So when I go to transform it, I'm going to use those points, okay? So my rule for this one is I'm going to add 2 to my x values, and I'm going to add 1 to my y values. And if you're not sure why it's add 2, there is a lesson on that from chapter 1. I think it's chapter 1. Okay, let's just go ahead and graph since we're here. This is moved up 1, so I'm going to move my asymptote up 1. All right, and then I'm going to use my rule to get my new points. So I need to add 2 to the x value, so that becomes positive 1. I'm going to write it down so I don't forget. And then add 1 to the y value, so that's 1 1/3. 1, 1 and 1/3, right there. For 0, 0, add 2 to the x value, that's 2. Add 1 to the y value, that's 2. So we got 2, 2. And then for my last point, 1, 3, add 2 to the x value, that's 3. Add 1 to the y value, that's 4. So 3, 4. So here is my exponential growth function. My y-intercept, 0, comma. I didn't figure that out yet, so I got to do it. Plugging in 0 here, 0 minus 2 is negative 2. 3 to the negative halves, or sorry, 3 to the negative second power is 1/9. 1/9 plus 1 is 1 1/9, or 10/9, either one. Domain, all real numbers. range, the lowest it goes is my asymptote of 1, goes forever up, asymptote y equals 1. All right, one more and then pause the video and try the last two on your own. So this is the parent function here is y equals 1/3 to the x. So I need to get my 3 points for that. -1, 3, 0, 1, and 1, 1/3. Not hard to get those points, right? But I don't trust my brain just to think about them in my head. All right, my rule. Subtract 1 from your x values, x minus 1. Remember, we always do the opposite of that. And then y minus 4. Okay. All right. Asymptote, y equals -4. All right, my new points. I'm going to subtract 1 from the x value, -2. I'm going to subtract 4 from the y value, -1. -2, -1. Oops, that's not -2, -1. This is. No, it's not. This is. All right, 0, 1, we got -1, -3, -1, -3, right there. All right, and then the last one, plugging in 1, 3, I get 0. Plugging in a third, I get -3 3/4. Nope, that is terrible. -3 2/3. All right, 0, -3 2/3 is right there. I can see that this is exponential decay now. I could tell before I graphed too. My y-intercept, I already found it. It was 0, -3 2/3, or that's -11/3. My domain, all real numbers. My range is -4 to infinity. And my asymptote is y equals -4. Okay, how'd you do? I feel like I did just fine. I want you to pause the video and try these last two. Notice it's no calculator. Okay, all of this. And then start it back up when you want to check your answers. I'm about to do that. I didn't copy and paste anything, right? Yes. Okay. All right, now I got to figure out where this goes. There looks good, right there. Okay, so let me zoom out so you can see it. There are your graphs. That's what they look like. All right, now it's time for you to practice.